太棒了。好，那你在那边操作吧。那我这边换页组，我就从这里换了哈。
我问一下，
好，那这个好。Okay, let us begin our class today. Today, we'll talk about the ordinary differential equations. Ordinary differential equation is very easy for everybody, all right? But we'll focus on the physical meaning of each differential equation we introduce here. All right. So we have ODE of motion. Then what do we mean homogeneous ODE in physical meaning? What do we mean non-homogeneous ODE? Then we talk about couple ODE, concluding remarks. Okay, rigid body. Everybody knows a rigid body. Why should I talk about rigid body? Right, Newton law. That's the easiest physical system we have. As a rigid body move in space, for example, assume we don't have any aerodynamics, no air, we move in space. It is a free motions, one direction only. We have a force applied to a mass m. Then where is this mass supposed to go? Would you think that's easy enough? That's a high school problem, right? And may not be high school, even lower than high school. All right, this is Newton law. M d squared x1 divided by dt squared equal to f. That's force. Or we just write m x1 double dot equal to f. Now, no. M must be larger than 0. Can I have m less than 0? So in this differential equations, m must be larger than 0. We call positive value. Later on, we might have the matrix, mass matrix. Well, we'll have a mass matrix rather than just only a scalar m. And we'll talk about that later. It's important. Now we can write this second order equation to become first order equation of motions. Agree? x1 dot equal to x2, then mx2 dot equal to f. That's the same thing as mx1 double dot equal to f. Why we want to do this? And I explain to you now, right now. Now we call this matrix equation of motions. In this class, we'll deal with only first order equation of motions. We don't really look at second order, although in general, any mechanical system is a second order equation of motions. Agree? Do you have any example? A mechanical system is only the first order equation of motions. Anything? Any example on that? I don't think so, right? Anybody from mechanical engineering department? Are you? Can you think any first order equation of motion for any mechanical system? No? True. So we are talking about the second order equation of motion for any mechanical system. However, in control theory, it's all developed. Any method, any control method, is developed based on first order equation of motions. Well, I wouldn't say all of them. I would say most of them. So we need to talk about the first order equation of motions. Now, if we have a second order equation of motions, we want to convert it, become first order equation of motion, then it becomes matrix equation of motions. So first order. What's my first order? Look at this first order. This is the simplest first order equation of motion for any mechanical system. What is the significance of this? That's what we're looking for. We have a matrix 0, 1, 0, 0. Okay, now 0, 1, 0, 0. There's a name called defective matrix. All right, then we need to explain what we mean defective matrix. Have you heard eigenvalue of a matrix? Anybody? Eigenvalue matrix, right? Heard about it. If you never heard about eigenvalue of a matrix, please raise your hand. No? Okay, that's good. So I don't have to refresh your memory about matrix then. All right. What is the eigenvalue of this matrix 0, 1, 0, 0? What is this?
可以用黑色笔写。
Okay. We need to try it again. I need to use the bracket. Yeah. All right. What? Are the eigenvalues of 0, 1, 0, 0? What are they? Anybody? No? You don't know? This is simplest way. It's the simplest matrix you can ever have. 1? You think so? Huh? 0? 0, 1. Or 1, 0, 1, 1. How you solve the eigenvalues? So that's supposed to be lambda I minus, if I call this is a matrix A, minus A, the determinant of that equals 0, right? Agree? That is lambda. That is lambda 0, 0 lambda minus 0, 1, 0, 0 equal to 0. That is lambda 1, 0 lambda minus 1, then determinant equal to 0. That means lambda square what? Equal to what? Right? Agree? That's how you solve eigenvalue, right? This is the determinant. This I means 1, 0, 0, 1. So I try to refresh your memory about this. Okay. Now, look at this. Lambda square equal to 0, that means what? How many zero you have? 2 zeros. Aha. Don't forget about 1 0. You have 2 zeros. 2. No, not 1 0. 2 zeros. For a matrix of 2, 2 by 2 matrix, 2 by 2 matrix, there are 2 eigenvalues. So we're 2 0. That 2 0, what we mean is we call repeated eigenvalues. The eigenvalue repeated. Okay. This gives you a very important information. For any rigid body motion like this, we have 2 zero eigenvalues. So you gotta memorize this, because that is a good problem for our midterm exam, right? 2 zero eigenvalue. If you say, oh, eigenvalue is 0, that's not right. You have to say 2 zero eigenvalues. They are repeated. Then I will show you those repeated eigenvalues, what kind of solution you're supposed to have. So you must remember that the rigid body motion has 2 zero eigenvalues. So if I say your system has 2 zero eigenvalues, then you will tell me that that is rigid body motions. Okay? So that's rigid body motion. This is the properties of a rigid body motions. This is also very important, I call properties of a rigid body motion. So eigenvalue is 0, 0. The eigenvector is 1, 0. But we have 2 eigenvalues. We only have 1 eigenvector. I don't have 2 eigenvectors. Why? Why have I only one eigenvector? We're supposed to have two eigenvectors, right? We are missing one. We have one eigenvector. Can you give me second one? Is there any second eigenvector for this problem? The answer is no. That's what we call defective matrix. This matrix is defective because we have 2 eigenvalues, but we have only 1 eigenvector. Then I will show you what is the significance of losing 1 eigenvector. If I have 2 eigenvectors, that make my problem easier. Right? The matrix 0, 1, 0, 0, this kind of defective matrix, they always short of number of eigenvectors. What does that mean? That means 0, 1, 0, 0 is the simplest matrix form you can ever write for these motions. Okay, now second one, for any matrix, for any system, for any system to be controlled, we have 2 equations. One is we call matrix equation of motion. One is called measurement equations. If you have one sensor, you have a sensor to measure any motion of a system, then you will have a measurement equations. All right. So this matrix equation of motions, another name we call state matrix or state equations. All right, you write it down. All right. In control theory, the matrix equation of motion is called as state equations. So we call state equations. There are two states, x1 and x2. So we have two states, x1 and x2. So in matrix equation of motions, for a single degree of freedoms, for rigid body motions, we have two states. Right? This is single degree of freedoms. Agree? Now we have two states, one x1, one x2. What is x1? What is x2? You tell me what is x1 and what is x2. What does that x1 mean? S1 give you what? Give you displacement. X2 give you what? Velocities. Yes. So for any single degree of freedoms, you have two states. One give you displacement. One give you velocities. So we call two states. The measurement equations. What's the measurement equations? If you measure displacement x1, if your measurement is displacement, we call y, that's my measurement quantity, equal to x1. If your measurement is velocities, that y will be equal to x1 dot, also equal to x2. So depend on what kind of sensor you use. If you use a displacement sensor to measure your motions, then your y, that's my measurement quantity. The y, I give you a census. I don't tell you what kind of census I'm going to measure, and what kind of the quantity I'm going to measure, what kind of state I'm going to measure. Then we all use the y, this y symbol, to represent the measurement equation. Y is a quantity. That quantity gives you a measurement. Now you gotta look at this very carefully, because y, for any measurement, what kind of quantity you will have. I give you a measurement, what kind of quantity I have. From any electronic device, you get what? You get a volt, you get amps. You are not going to get meter. You are not going to get a centimeter. You are not going to get any physical unit. You will get what? You will get either amps or volts, right? Then you can convert it. So that's why, this is why we use y to represent x1, or use y to represent x1 dot or x2, because we give you only the quantity which is not physical quantity, which is in the electrical unit, either volt or amps. Understand about that? All right. So I give you three different choices. The first choice is displacement. All right, we call y equal to x1. That's measure of displacement. All right, y can be also x2 equal to x1 dot. That we call velocity measurement. Let's go velocities. All right, if I give you the y equal to x1 double dot, y can be x1 double dot. If I use accelerometer, and then you measure the accelerations. Now the x1 double dot equal to 1 over m1 f, right? M. There's no m1, just m. So actually, if you use accelerometer to measure the accelerations, you really get the quantity of f divided by m. And this f is the force. And this 1 over m, normally we define that equal to a d. We call d. Why was d? D means direct transmission term. In control theory, we call D is direct transmission terms. That means you direct transmit the force to your measurement quantity. You measure, you got a force quantity. Do you see any state there? No. There are no x1, there are no x2. So if you use call accelerometer measurement, then you don't get the state in your measurement equations. No state x1, no state x2 there. None. Zero. You only get the direct transmission term. Now listen carefully. If you use the displacement sensor, then you have x1, the displacement state there. If you use the velocity sensors, you get the velocity state there. If you use the accelerometers to measure the accelerations, then you don't get in a state. Instead of you getting in a state, you get direct transmission term. So if I give you XM problem, I say, I'm going to use the accelerometer to measure the motion quantities, then what do you get? You get direct transmission term. You don't get any state for rigid body motions. I'm talking rigid body motions. Okay? All right, so this is in here. I explained to you called displacement, velocity, accelerations, and direct transmission term. Any questions? I'm going to introduce you the three basic motions for mechanical systems. This is one of them, called rigid body motions. And rigid body motion has two zero eigenvalues. Rigid body motion has a defective matrix. Rigid body motions, if you use the accelerations device to measure your motions, then you have direct transmission terms. All right, I give you all kind of message now. Let us look at called vibrational motions. Any system, any engineering system is a combination of rigid body motions and flexible vibrational motions, and then I have another motions. I'll show you next slides. And I will tell you all the significance of these motions. Vibration motions, that's very simple. Now, a rigid body M, I link with a spring. And what happens? The second equation of motion, second order equation of motion becomes this. mx1 double dot equal to minus kx1 plus f. So we have now minus kx1 involved in our second order equation of motions. Right, the rigid body motion means k equal to 0. By Newton's law, for any rigid body motions, if you don't give them any force, then they either stay still or keep moving in a constant speed, right? But if I have the spring K here, then they go nowhere. We'll come back. They won't have a constant speed anymore. You let it go, right? Okay, let us look at the first order equation of motions. Look at this first order equation of motions. Now I have x1 dot equal to x2, mx2 dot equal to kx1 plus f. My matrix equation motion now I have x1 dot, x dot, 2 dot, and 0, 1 minus m inverse k 0. Then plus 0 m inverse 1. Okay. Now what is the eigenvalue of this matrix? So in control theory, if you want to know more about control things, then we gotta understand the eigenvalues, and we gotta understand what eigenvalue will give the system. What is the eigenvalue of this? All right, that's the eigenvalue of this. What's the eigenvalue of this? What are the eigenvalues of 0, 1 and minus m1 k 0? What is the eigenvalue of that? Assume, let's say that. That m1 inverse k equal to omega square. That means 0, 1 minus omega square 0. Eigenvalue is what? Tell me. Huh? Could solve it.
Omega.
Huh?
Omega.
Number omega is, one is I omega, another one minus I omega, right? Agree? Now I have two distinct eigenvalues. However, now these eigenvalues, I have I there. This is imaginary. This is not real quantities. Right? Agree? What does that mean? The complex I here. This I represents square root minus. Now, in real world, what do we mean I? What do we mean? In the real world, what is square root minus 1 meaning? What is that? Can anybody tell me? In the real world.
Face.
Huh?
Face change.
Questions?
Face.
Face?
Yeah.
Oh, face.
Face change.
Sounds good. Face. Well, the I is really in a mathematical meaning. Physically, there are no such imaginary axis. No. So I here just tell you, oh, my eigenvalue as I. Mathematically, because from second order I become first order, then I have, unfortunately, if I want to solve this lambda square plus omega square equal to 0, then that's so that's the solutions, right? No, but in real world we know what? We know if we have spring there, our frequencies is omega. If this spring is oscillating, they're oscillating with the omega frequency. So this is frequencies. Omega means frequencies. In mathematically, the root, we have I, minus I here. Why we have I here, we also have a minus I here. Oh, because this solution gives you a knot, right? It's 1 I omega, 1 minus I omega, right? But there's some meaning there. All right? How many states we have? How many states in here we have? 2. State x1, state x2, right? Okay? All right, state x1, the oscillating frequency is what? Omega. State 2, the oscillating matrix is what? Omega. But you are right, they have a phase difference. Because one is I, one is minus I, means they have 180-degree phase difference. Okay? Understand now?
Yeah. Sorry to add.
Okay, go ahead.
Might be stupid anyway. Though I know it's face, we call it face, but physically I really don't imagine or have the picture of what that face really means.
I'll show you. Yeah, if you displace move this direction, your velocity is supposed to be in other directions. That's what it means. That's the directions is different. Your state moving different direction is different. All right, I show you the some of the motion here. All right. The same thing, the measurement equations. Y equal to x1. If you have a displacement, then y is 1. We have a velocities, and then y is x. Then, well, in the spring here, I have to give you a spring there. Look at that spring there. All right. If you look at this system, vibrational motion with a spring there, the spring will never stop. If you give them initial conditions, then they will never stop, right? Assume that we don't have force there. So they will keep moving like that, in theory. Now, the only difference is in the measurement equation here, if you look at carefully, the measurement equation here, if you use acceleration measurement, then you will have a state there. In a rigid body motion, you don't have a state there, right? I show you. If you have y equal to x1 double dot, for rigid body motion, you have only direct transmission term here, there. But if you have vibrational motions, then in addition to the direct transmission term, you also have a displacement term involved in there. You gotta be very careful about the third equation, y equal to x1 double dot equal to x2 dot equal to, then I have a minus m inverse k x1 plus m inverse f. So we have two terms. If you have direction, if you use the acceleration measurement, then you have the state term, that's a displacement term involved there. You also have a direct transmission term there in your measurement equation. So we have a measurement equation. You've got to be careful for this. Now, on the other hand, if you obtain a measurement equations which show you have only direct transmission term, that means you are doing what? You are doing a rigid body motion measurement. You have two terms involved, direct transmission term, plus you have displacement term involved in there. You will know that that is not rigid body motions. That is a vibrational motions. Okay? So, we are talking about ODE. We are not talking about ODE mathematically. We are talking about ODE physically. We must understand all the physics for this kind of simple motions. Think about it. For any mechanical system, even the building like this, it is civil structures. It's nothing but the combination of rigid body motions and vibrational motions. Agree? Right? All right. Now let's look at the third motions. All right. Now let's see what else. Well, there's if you use the MATLAB or use any software to solve this equation of motions, and then they plot your curve, will be look like this. The motion will be looked like this. All right. That's if you look at the displacement, you look at the velocities, you look at their directions, you can see that their direction is different. They're moving in a different location, the different directions. If your displacement is increasing, your velocity is decreasing like that. All right, that's the equation of motions for d squared x1 divided by t squared, then plus 2 pi, then parentheses square x1 equal to 0. That is the vibrational motions, and it vibrates like this. Let's give you some of the idea. Now, this is the third equation of motions you need to learn. Vibration motion with damping. By the way, all the notes, you can download it from our website. It's all there. So I put about 3 or 4 chapters already down there. For any file, any slides, the set of slides, if the file is larger than 1 megabyte, then I put in the I call what the guest. What's the name of that? In that because I cannot upload it. It exceed 1 megabyte, I cannot upload it, so I give you the website to download it. All right. Anyway, you can download it from those. All right. Now we have these third motions. And look at carefully that the first one we have 0 eigenvalue. The second one, the vibrational motion, we have a pure imaginary eigenvalues. The vibrational motions. Now, if we have a damping, we'll see what happens. Now, so here we have a Newton law involved here. We have Hooke's law involved here. We have viscous dampings involved in here. And that equation of motion is very simple. It's mx double m1 double dot mx1 double dot equal to minus kx1 minus cx1 dot. Now we have a minus cx1 dot plus f. Oh, I forgot that one important comment here. M must be larger than 0. C, the damping coefficient must be larger or equal than 0. The K, the stiffness, the constants, that also must be larger than 0 or equal to 0. They cannot be negative. Neither M nor C or K can be negative. That's important because we will use that to design controller too. That information. So the first order equation of motion is like this. Now my matrix equation of motion now is different. I have 0, 1, minus m inverse k, minus m inverse c. Now, okay, the same thing. What eigenvalue of this? What are the eigenvalue of this? Minus m inverse c. Eigenvalue of this. Anybody tell me what eigenvalue of this? Now we talk about, now this is the third matrix talk about it. The first one, 0, 1, 0, 0. That's the rigid body. The eigenvalue is 0, 0. And the second one, we have 0, 1, minus m inverse k 0. The eigenvalues is pure imaginary. Right? The third one here, eigenvalues. The eigenvalue is pure imaginary. The third one here, eigenvalue. I'm not going to solve for you, but I will tell you. Now, this eigenvalue will be complex eigenvalue. This eigenvalue has real part, plus or minus I, imaginary part. The eigenvalue of this matrix, it includes two eigenvalues with a real part and imaginary part. And also plus or minus, they always come with a pair. If you have plus I, you also have a minus I. All right. Then what does that mean? The real part eigenvalue. What I mean, the imaginary part eigenvalue. Imaginary part eigenvalue, just give you frequency. The real part eigenvalue just gives you damping. All right. So when you solve the eigenvalue of this matrix, you look at imaginary part, then you will know that that is my frequencies. You look at real part, is I say that is my damping. If m larger than 0, c larger than 0, and k larger than 0, then you will have the eigenvalue like this. You have damping terms. You have frequency terms. So those eigenvalues give you the real system properties or real system characteristics. Because they give eigenvalues, they give frequencies, they give you dampings. All right. So when you solve the eigenvalue of matrix, then you are to interpret what this eigenvalue mean to the system. You can just deliver to me. Your teacher will say, "Hey, that's my eigenvalue. That's it." I don't do any good, right? If you go out to the company, you tell your boss, "Oh, this problem, I keep eigenvalue. That's my complex eigenvalue." He doesn't want that. He want what? He want you to tell him what kind of frequencies I get, right? That's important. The physical, I call the physical meaning of the mathematical eigenvalues. All right. Now, the measurement equations. The same thing. X1, X2 is the same thing. If you use the measurement device X1, then you got a measurement. If you use the measurement, you use the velocity measurement, then you got the velocity X2. You got the velocity quantities. But if you use the accelerations measurement, then you have the X1 term, you have X2 term, you have also the direct transmission term. So the measurement equation gives you the differences in different motions. Right? Remember that. When you have a measurement equation, somebody show you that my measurement equation has X1 term and X2 term and direct transmission term, that means I'm using accelerometer to measure the motion quantities. Because if you don't use accelerometer to measure the the motion of the system, you really don't get any direct transmission term. Agree? So measurement equation is important here too. All right, so I introduce you 3 basic system motions. I call basics, or we call fundamental motions. 3. There are no more than these 3 for any mechanical system. All right. So any mechanical system. Let me show you. Let me just in summary. Any mechanical in summary. Any mechanical system equal to which body any mechanical system where I have a rigid body motions plus vibrational motions plus vibration motions with damping. That's it. So in the control, this class, we are dealing with a mechanical system which may have rigid body motions plus vibrational motion plus vibration motion with them. That's it. No more than that. Cannot have more than that for any real the mechanical system. There was 10 minutes break. 休息10分钟。